So what we're going to be looking at today is volumes by slicing. This whole section, we're going to be looking at volume, this whole chapter actually, we're going to be looking at volumes, we're going to be looking at surface area, we're going to be doing all those kinds of things. And so today we're looking at volumes by slicing. So first off, the objectives of this particular section are to learn how to do the volume of a solid, where we just use the slicing method, but then we also are going to do some volumes of revolution. So that means we're going to be revolving some regions about the X and Y axis and being able to determine what the volume of the resulting thing is. Okay, so as you know, if I take a deck of cards, let's just take one card. All right, I can find the area of that one card. It's flat, it gives me area. But if I stack all those cards up and just keep stacking them, then eventually they give me volume. So anytime you take an area and you extend it in any direction perpendicular to the area, you're going to get volume. So our volume is always going to be the integral from A to B of the area defined as a function of x dx, or it's going to be the integral from C to D of the area defined as a function of y. Okay, it just depends on whether it's in the x direction or the y direction. So the first thing we want to do is volume by slicing. And so I did spend a little bit of time trying to draw some figures here. So let's suppose, as you can see, we're going to look at this picture on the left. And I have drawn the three-dimensional axes. This is the x-axis. No, this is the y-axis. This is the x-axis coming out. And then, of course, this is the z-axis. So as you can see, I have a rectangle in the xy plane. And so a rectangle in the xy plane has a base. All right. And so that base has a particular area. And so the area of that base is here. So I'm going to write base right down here. And so this is a particularly easy one. This is, you can see that the x goes from 0 to this value of A. And then y goes from 0 to whatever this function is, y of x. All right, so if I wanted to compute the area, I would integrate, just as a basic area problem, I would have 0 to A, and then the base, the y value goes from 0 up to y of x. That's going to give me the area of the base. Okay, so now that I know the area of the base, what I'm most concerned about is what are going to be my cross-sectional areas or my slices. Okay, so the problem is going to tell you what the base looks like inside of some function y of x. And then it's going to tell you that at each value of x, you are going to have an area. So at this value of x, let's say I choose this value of x right here. And at that value of x, I'm going to take this area and slide it right over. And so I have an area that is perpendicular to my base at that value of x. So that area that I know that for that area, whatever the height is, you need to tell me the height, and then you need to tell me how long it is. But for that given x, the length going along the base is y of x. So whatever x is, if x is 2, then that's y of 2. Then I'm also going to take this and I can do the same thing for another value of x. And so let's say I choose this value of x. And I stick, of course, I can't get that in there perfectly. My hands are shaky. Come on, Dolan. This worked better when I was doing it earlier. Okay, there we go. And then here, so now you can see that now you can see that the cross sectionals are rectangles. So for each slice, the cross sections are rectangles. And I can see that the length of the base at any given X is Y of X. And then somebody needs to tell me what the height is. Once I know the height, then I know the area of each one of those rectangles. It's going to be the length times the height. And then my volume will simply be the integral from 0 to A. I should have called this B. Let me call that B. From 0 to B of whatever I find my area to be dx. Okay. So that happens to be for that particular problem. So let's look at this problem over here. Here's a very similar problem. So in this problem, let's say the problem tells you that for any value of X, okay, this is the curve. Let's say Y is equal to the square root of 4 minus X squared. Let's say 4 minus X squared. So it's the top half of a circle, okay? The circle was X squared plus Y squared is equal to 4. It's the top half of the circle. This value is -2, X equal to -2, and this is X equal to +2, okay? And so the problem may say that this base is inside or underneath the curve Y is equal to the square root of 4 minus X squared. That's what the base is. And the cross sections perpendicular to the X axis are triangles. Okay, so it tells you, so at any given X, the cross section, so as you can see, I can put a triangle here. And then this one probably goes, I forget where I put it. Yeah, this goes here. Why was this so easier earlier? And then this triangle comes down here. So as you can see, if I were to continue to do this, I'm going to end up with something that's kind of round on the bottom, but pointed at the top. And if I did that for every X, I'd have a three-dimensional figure. And this three-dimensional figure, I can find the volume of it. So now if I want to find the volume of the three-dimensional figure, I need to find the area of the triangle. Okay, so let's do both of these problems. Okay, so well, actually the second one is more exciting. So I'm going to do the second one. All right, so here's the problem. So let's compute so here's the region. So we're going to consider the solid whose base is bounded by the upper semicircle X squared plus Y squared is equal to 4, and whose cross-sectional areas are equilateral triangles. So what I want to do is find the volume of the solid. Okay, so just from this picture, I already know that I'm going to integrate from -2 to 2 because my triangles are going to start all the way when x is -2, all the way up to x equal to +2. Because again, this is the x-axis, this is the y-axis, and this is the z-axis. Okay, anybody have any questions about what it is I'm trying to do? Trying to find the volume of this weird looking shape where the bottom is a semicircle, but as it's standing up, if you were to count all the slices, it's kind of like slicing a loaf of bread. And every time you slice a loaf of bread, you're going to see some type of area. Find the volume of the solid. Okay, so I already know my volume is the integral from -2, -2 to 2 of some area of x dx. And in this particular problem, it's symmetric. So if I want, I really only need to do 2 times the integral from, okay, y'all still can't see everybody, but 2 times the integral from 0 to 2. I really only need to do that much. Okay, because it is symmetric. So for this particular problem, not every problem, but for this one, I can do 2 times the integral from 0 to 2 of whatever my area is. So now the big part of the problem is to find the area. So it says to me that the areas are cross-sectional areas are equilateral triangles. Okay, so now let's draw an equilateral triangle. So I'm going to go up here and find an equilateral triangle, and I'm going to draw it as best I can. That's not too bad. So here's my equilateral triangle. This is the same triangle that appears in my picture. So as you see the triangle in the picture, so therefore, for any particular value of x, between 0 and 2, this length right here is on the curve. The height is on the curve. So therefore, the length of that bottom length, this bottom length has to be the square root of 4 minus x squared. Because this point right here is on the curve. So if I've chosen x, then the top value right here is on the curve. So therefore, that length must be the square root of 4 minus x squared. Okay. Well, this is an equilateral triangle. So an equilateral triangle means that all the lengths are the same. But how do you find the area of a triangle? So what I need is the area of this triangle. So A of x is going to be the area of this triangle. So what is the area of a triangle?
Isn't it 1/2 base times height?
Good. All right. So area of a general triangle is 1/2 the base times the height. Okay, so as we can see, our base, we already know our base. Our base is the square root of 4 minus x squared. So this is the equilateral triangle, so we need to find the height. Okay. So for this to be the height, we now know that this is going to come down right at a 90-degree angle. Okay, so for that to be a 90-degree angle, I already know what this side is. So this side over here is also the square root of 4 minus x squared. So that's what this side is. So this side is the square root of 4 minus x squared because it's an equilateral triangle and all the lengths are the same on the sides. But I also know that just this little piece right here, for that triangle, just this little piece, okay, that little piece is 1/2. So the base of that, so now I'm only going to work with this piece of triangle. So I'm only going to work with this triangle. And then after I figure out the area of this triangle, I'll multiply it by 2 to get the area of the whole triangle. So let's just work with this little piece right here. Because for this one, I can use the Pythagorean theorem. So I know that this little piece right here, this little red piece right there, that length is 1/2 the square root of 4 minus x squared. So now this is what I have. So now I have this little triangle I'm going to pull out. So I'm going to pull out this little triangle for a moment. So this triangle pulls out like this. So this is just the green triangle. So for the green triangle, this side is 1/2 the square root of 4 minus x squared. And this side is the square root of 4 minus x squared. And I know that a squared, if that's a, and this is b, and this is c, I know that a squared plus b squared equals c squared. And b is the height of my triangle. So this b, oh, I don't want to call, let's not call that b. Let's see, what do we want to call that? Let's just call it what it is. It's h. This is h, and this is b. Okay. So by the Pythagorean theorem, I don't want to confuse you. We're going to use h squared plus b squared is equal to c squared. So h squared is going to be c squared minus b squared. So c squared is just going to be to square that side. So that's going to give me 4 minus x squared. That's c squared. And b squared, the base squared, is just going to be 1/4 of 4 minus x squared. So I can see now that h squared is 3/4 times 4 minus x squared. So now I know h. So h is the square root of 3/2 times the square root of 4 minus x squared. So now I know the height. So now I know the height. So that's all I needed. Okay, all I needed was the height. So now we know the base of this whole triangle, the base of the whole of the equilateral triangle. So the base, so for the equilateral triangle, the base was the square root of 4 minus x squared. Okay, we said that because that's the whole base. 4 minus, that's L, the leg L. And then the height is now the square root of 3 over 2 times the square root of 4 minus x squared. And so now I know the area. So the area of the triangle is 1/2 the base, which is the square root of 4 minus x squared, times the height, which is the root of 3 over 2, times the square root of 4 minus x squared. So therefore the area is now the root of 3 over 4 times 4 minus x squared. Nice and simple. Okay. So now that we found the area, I know that the volume of the solid is the integral from -2 to 2 of the area of x dx. But we said that's the same as 2 times the integral from 0 to 2 of the area. But then that becomes 2 times the integral from 0 to 2 of the root of 3 over 4 times 4 minus x squared dx. So this is now the square root of 3 over 2, the integral from 0 to 2 of 4 minus x squared dx. So when I find the antiderivative, I'm going to get the root of 3 over 2. I'm going to get 4x minus 1/3 x cubed, evaluated between 0 and 2. So I get the root of 3 over 2. I'm going to put in 2, so I'm going to get 8 minus 8/3. So that's going to give me the root of 3 over 2. And then that's going to give me 2/3 times 8. So I'm going to get 8 the root of 3 over 3. Okay. So basically what you have to do for each one of these volumes by slicing is you need to find the area of whatever the slice is. So for this particular problem, the area of the slice is the area of the equilateral triangle, but I needed to find the area of that. It was 1/2 the base times the height. I already know what the base was. The base was the length. That was the base of the triangle. And then down here, this was 1/2 of the base. So that's what we used. We used 1/2 of, actually it was 1/2 of the base. Yeah. So this was 1/2 the square root of 4 minus x squared. So we use that in order to get C, the height. When we found the height, then we were able to now know that we know the height of the triangle. We could do 1/2 the base times the height, and that's the area, and we could integrate it. Okay. Any
Dr.
questions?
Locke,
Yes.
sorry to interrupt, but for the answer, do you expect us to put in, like, say, units, square, units, cubed?
If I had
Assuming
given them
if we,
to you, I didn't give you the units. So
Okay.
you don't know. If I had said, I didn't give you units. So if I had told you inches, then yes, you would need to use inches. But I didn't give you any units.
okay, thank you.
Okay. All right. So these problems, so the first thing I need you to understand is volume by slicing, you must find the area of whatever it is. Okay, so whatever the particular region is, you must find the area of it. Okay, so here's another problem. That one does the same thing. Okay, this is another example. So actually,
What's the third step after we found the height and we found the area again?
where in this particular problem?
So yeah. Oh,
Okay, so for this particular problem, what I did was I said, in order to find the area of this triangle, so
we
the,
already
pardon?
found it. Nothing. Go ahead. Simone.
I'm trying to see who's talking. Oh, there you
You
are.
talking, Shakla? Yeah.
I see it. Okay, so right here, we needed to find the area of the whole triangle, which is what we needed for this problem. Because this problem, each one of these things is a whole, each one of the cross-sectional areas is a triangle. So you have to know what the area of each cross-sectional area is. That's the A. So whatever's standing up in the air is, you have to find the area of that thing. Okay. If you can find the area of one slice of bread and then add them all up, you have the area of the whole slice of bread, right? But that's just adding things up is just the integration. So I needed to find the area of the triangle. So I'm trying to find the area of the whole triangle, which is 1/2 the base times the height. But we already know that the base of this whole thing lays just like that, where this point, this dot right here, is on on that curve. So I know that that length right there, this length, I already know is the square root of 4 minus x squared. I know that length. Now what I needed to do was I need to complete the fact that the area is 1/2 that length times the height. So now what I need to do is find the height. So once I get that the length is this, I now needed to find the height. So in order to find the height, I said, well, let's deal with only half the triangle. And then I can use the Pythagorean theorem because I have a 90-degree angle. So when I'm dealing with 1/2 of that, so now I went over to this little sub problem over here. So this little sub problem over here is where I'm just solving for the height.
No, we did that already. Yeah.
So in order to solve for the height, I have a new problem. So for this new problem, its base is 1/2 the square root of the whole length, the length I had before. And then because it was an equilateral triangle, this side, not what I want to do. I want yellow. This side is this side right here. So now I just used the Pythagorean theorem that h squared plus b squared has to equal c squared. So I was able to solve for what h is. Once I have h, I can now go back to the original problem, which was for the equilateral triangle, I had the base and the height. So once I computed what the area was, so so the steps for this problem, you need to identify the limits of integration. So let's see. Identify the limits of integration. If you identify the cross-sectional area, then find a formula for the cross-sectional area. And then substitute a of x into the integral. So these are the steps for volume by slicing.
Thank you for going
You're
over that.
welcome.
Okay.
No problem. Okay, so as soon as this video comes to me, I will go ahead and I will post it for those who do wish to watch the video. Okay, any questions?
Hi, Dr. Lack. Would you kindly go over the part where we were going from the integration of -2 to 2 to 0 to 2?
Okay, so the
That's the part.
picture is, so if you go back to the picture, it's symmetric. So it's going to have the same triangle. It looks the same from -2 to 2 that it does from 0 to 2. So the area, the volume is going to be the same. So instead of me going from -2 to 2, I can do twice 0 to 2.
Okay, that's just so you didn't have to deal with the negative sign.
Exactly. That was one thing that helped. Yes.
All right, thank you very much.
Okay. All right, so the question on the due dates for Edfinity, they do not close until the last day of class. So the due dates on Edfinity close on the last day of class. Okay, after the due date, you do lose 20% though, but you can still do the problems. Okay. All righty, I think that's it. I'm going to stop recording.